Hello everyone, welcome back. We started solving some numerical example and I picked up a problem that was more complex at the beginning itself. So I thought about it again and I have prepared some more simpler problems with simple 1D flows and not with so much of area change. We will go and do that kind of problems again later when we go to nozzle flows calculations. We will go and do it later. But currently we will just go for more simple problems. So we will pick up some example. I am having a shock in a straight area constant area duct, and we know that pressure here flows this way, pressure here is 1 bar and pressure here is 2 bar. This is the information I know, and now I know that the gas is air. When I say this, gamma equal to 1.4. Now my idea is to find the shock Mach number, find we know the pressure ratio, I want T2 by T1. I want the post shock Mach number and delta S by R. These are the things I want. Okay. All this we want to find. So how will I do this? Straightforward question. We know something about the shock, that is the pressure jump across the shock is given. So we already know that normal shock tables will have P2 by P1 as one of the columns. Okay. So all I have to do is find P2 by P1. It happens to be 2. So now I have to go to normal shock tables for gamma equal to 1.4 and find at what row it comes out to be P2 by P1 equal to 2. If I do that calculation, I am going to get M1 approximately equal to 1.36 with a little bit of approximation. Its number happens to be 1.996 or 997, something like this. I have the tables, I can look at the number, but anyway I have done this work, just look at it. So now we know that this is the shock Mach number. Of course we want other properties. M2 directly in the same row, I just have to read out the next column. M2 is just another column there, that value happens to be 0.757, and if I read out T2 by T1 from there, T2 by T1 is 1.229. So I am getting answers directly, that is why I told it is a very silly problem, simple enough problem. Okay. And then now I want delta S by R. What is delta S by R? Is equal to log of P01 by P02. We proved this already. So now I am going to pick this up and we want to find P01 by P02. My gas tables, whatever I have, the compressible flow tables, whatever I have gives P02 by P01. Okay. So I will write that as log of 1 by that ratio. That ratio for this particular Mach number for gamma equal to 1.4 comes out to be 0.968. And so my delta S by R 0.033. That is your answer. I can do this the other way also. I can say that delta S by R equal to minus log of P02 by P01. I will get the same answer anyway. Okay. So this is a simple enough problem. We solve this. Now what if I say that my gamma is not 1.4, it is not air, but it is argon. If it is argon, it is a noble gas, gamma is 1.67 or 5 by 3, okay, 1.66 or 1.67, whichever you pick. So I want to go and solve the problem with some other normal shock table, but exact same procedure. P2 by P1 is still 2. So, my M1 I am going to find the closest match, that happens to be 1.34 for this particular gas. Okay. And so, now I have to just read out the next value M2 0.774, T2 by T1, again read out the value 1.331. Now, the next one I have from my tables is P02 by P01, which happens to be 0.974. So, I am going to delta S by R is minus of log of this number, which happens to be 0.026. What is the unit of this delta S by R? Delta S by R is per kilogram? No, it is not. What is the unit of this delta S by R? What is the unit of T2 by T1? Dimensionless. What about this? What is this equal to? Delta S by R is equal to log of P01 by P02. This side is dimensionless, so this should also be dimensionless. If it is a good equation, if it is a correct equation, both sides should have the same dimensions. So, this is also dimensionless, okay, which means what is the dimension of my entropy? Same as R. What is the unit of R now? Joules per kilogram per Kelvin. Okay. So, this will have units of entropy per kilogram. Okay. Remember that. The next problem I am going to give is based on that. So, we will go into that immediately. So, we will look at the next problem where we are giving something different. I am given P1 1 bar, T1 is 300 Kelvin, M1 is given to be 2, and I am telling you that there is a normal shock sitting inside my duct. There is a normal shock sitting inside my duct. If I have such a case, I am telling you this air gamma equal to 1.4, I am solving this problem, and I want you to find entropy change per unit mass for the air passing through this shock. That is what I want. I want delta S in per mass basis. That is what I want to find. So, how will I do this problem? I just have to go to M1 equal to 2 for gamma equal to 1.4, that tables, normal shock tables, gamma equal to 1.4, and I look at the row which has M1 equal to 2. There I will go and look for P02 by P01, that is what my tables have. There are tables which give you P01 by P02, mine has P02 by P01. So, this number for that case happens to be 0.721. So, my delta S by R happens to be equal to minus log of 0.721, which happens to be 0.327. We just now discussed this. So, delta S is equal to R times this value, where R is my per kilogram basis gas constant. So, delta S will be 288.6 into 0.327. I am saying it is air. Okay. So, it is 288.6. So, that is going to give me a number 94.45 joules per kilogram Kelvin. That is what I will get. Okay. Or I can look at this as joules per kilogram is typically units for entropy, is joules per kilogram joules per Kelvin, sorry, joules per Kelvin is the entropy units divided by kilogram, which is entropy per kilogram, entropy per mass, that is what you are getting. Okay. That is another way of looking at it. Let us say I do not want it in terms of per kilogram, I want it per mole. What will it be? How will I find per mole basis entropy change? Now I will write it, this is per mass. Now I want delta S per mole basis. What will that come out to be? How will it? I am not hearing what you are saying. So, okay. So, multiply this with molecular mass, that is one way of solving the problem, right. I already know the value 94.45 joules per kilogram Kelvin. This is per kilogram basis, per mass basis. Now, if I multiply this with mass by mole, I will get to correct units. So, I am going to multiply this with molecular mass of that particular gas, then I will get to the answer, multiplied by 28.8 into 10 power minus 3 kilogram per mole. Of course, you should know that molecular weight of air is 28.8 grams per mole. I have rewritten this like this. So, if I do this multiplication, I will get to 9 times 0.2 or something, which will be roughly 1 by 5, around 2, I am getting the answer, 2.72 joules per mole Kelvin. But this is because I already have this delta S per mass, I got this way. What if I did not have this already? How will I solve this problem? Will I go and solve this and then solve this? Unnecessary. This, look at this, I can rewrite this as, this is also equal to delta S cap by universal gas constant, is not it right? I am multiplying and dividing by molecular mass, that is all I have done from here to here, okay. That is also true, where S cap is entropy per mole basis. So, that is what I wanted to find. So, I can write it as delta S cap is equal to universal gas constant times that minus log P01 P02 by P01, which is 0.327. 8.314 multiplied by 0.327 will also give you this number. It is all the same, if you look at the actual math that is happening, it is all exactly the same, you will get to the same spot. Another way of looking at it, this R can be rewritten as this R multiplied by molecular weight, divided by molecular weight, divided by molecular weight will come, okay. So, I will write this as universal gas constant divided by molecular weight will go to the top, and that will exactly be looking like this finally, multiplied by molecular weight, you will get to the same spot, finally answer will be the same, okay. Various ways of looking at it, final answer is this, okay. We will go to some other question. Okay. Now, I am going to go to more practical problem. I am having a wind tunnel, supersonic wind tunnel. I will not tell you why the static pressure is measured one particular way, stagnation pressure is measured one particular way. Let us assume those are all correct. I am going to tell I have a side port on the wall and it is measuring pressure, and I call this static pressure. Why am I calling it static pressure? Just believe me, right now it is correct. It is called static pressure and it is static pressure. And I am having a pitot probe, we discussed pitot probe already, okay. The flow is coming here and it is slowing down to come to stop inside the tube, and so I am going to say the flow is forced to come to rest inside this duct. So, I am going to call it close to isentropic, and so it is isentropic flow, isentropic pressure finally at stagnation condition. I am going to call this, actually I should call it P0 only, I do not want to call it P02 already. I will just call it P0. Now, I am going to say I am having air flowing supersonic. Let us say I know this already, it is supersonic flow and I know it. If I know it, okay, I want to find the Mach number here given these two pressure values, that is the goal. One thing about supersonic flows, if it is stopped by anything, there will be a shock in front of it. In this particular case, the shock looks like this, we will go deal with it later after we go to 2D problems. Okay. But as of now we will just assume I get a shock like this, okay. Like 2-3 weeks later we will get into this problem. As of now we will just continue like this, and I am going to say flow through the center is what is going through the tube, and because of that it is seeing almost a normal shock in front of it, and if it is seeing a normal shock in front of it, the P naught is going to be decreasing across the normal shock. So it will not be P naught 1, but it will become P naught 2 on the other side. So whatever I am measuring here will become P naught 2, it is not stagnation point upstream of the shock, it is stagnation pressure downstream of the shock. So these are the numbers which I will practically measure if I put some pressure measurement device here. Let us say I am doing that in my lab and I am getting these numbers. P1 is 0.255 bar. I am giving you numbers that are close to what can be achieved in our lab. P02 comes out to be 1.44 bar. Now we want to find Mach number from here. It so happens that I have a good compressible flow tables, okay, where there is one extra column given P02 by P1, this is given in my normal shock tables. If I have this column given, very easy for me to solve this problem, okay. All I have to do is take this ratio, that ratio happens to be 5.647. Now I will just go to that particular column and gamma equal to 1.4, I said it is air, gamma equal to 1.4, and I want to look for this number in that column. Wherever it happens, I will just read out my M1 value, and that value is approximately equal to 2. It actually comes out to be 1.999, we will just keep it 2, that is what it comes out to be. Okay. But let us say I do not have that good gas dynamics tables, how will I solve this problem? That is the next question. Okay. If I do not have that and I have only these columns P02 by P01 and P2 by P1, these are the tables that I have, let us say, and I still want to find this, how will I find it? P2 by P1 does not help because I do not have P2 value, okay. It so happens that I do not have P01 also, but I have P1, okay. So now I have to do something else, I have to link P01 and P1, I do not know P2, we will eliminate this, okay. Of course I could link P02 and P2 also, but we want upstream condition M1 to be figured out. So we want link these two, we want to link P01 and P1. How will I link that? P01 and P1 is a function of M1. Why? It is isentropic flow. Yeah, if I pick a flow here, it is having this static pressure and it is having some stagnation pressure. If I take this flow isentropically through an imaginary process and make it stagnation, it will become P01. So I will take it that way and find the Mach number upstream, that will be a function of M1. We know this formula, in fact it is 1 plus gamma minus 1 by 2 m square the whole to the power gamma by gamma minus 1. That is something you should just remember, should just come into your mind from now on. Okay. Of course this is given in tables, you do not need to remember the formula really if you have tables in hand. Anyways, I know this and I know this is also a function of Mach number. This is coming from normal shock tables, this is coming from isentropic flow tables. Now all I have to do is start guessing, guess a Mach number, find, I want P02 by P01, P02 by P1, this is equal to P02 by P01 into P01 by P1. Now if I guess the Mach number, I can get this number and this number, this coming from normal shock tables, this coming from isentropic flow tables. Now my job is simple, I just have to form a table and start guessing numbers. Yeah, I will do that in the other board, and I have to reach the final P02 by P1. You know the answer now, so you know how to guess correct answer, but let us say I do not know, we will assume I do not know that M1 is going to be 2, because that is what you will be ending up when you are solving problems in exams. So, we will assume some case like that. I am going to guess a Mach number, okay. I am going to guess a Mach number, I will find normal shock tables value, I will find isentropic tables value, and then I will multiply these two to get this number, and I want to see whether this is matching my, I am looking for P02 by P1 equal to 5.647, this is what I want finally. So, let us see if it is possible. So, initially I do not know what to guess, of course typically I will guess 2 first, since I know the answer is 2 I do not want to guess 2 first, because I want to go through the iterative process. So, I am guessing 1.7, okay, nice number to guess, always remember guess 2 initially, in exams typically the number will be Mach 2, okay. So, if you guess 2 you will be close to the answer already, easy to solve, iteration will be less time, okay. If it is 1.7 then I am going to get 0.856, and in my tables it happens to be P1 by P0, that is what is given for me, okay. P by P0 is what is given in my tables. So, I just write numbers like this, I just write it inverted, okay. Now, I have to multiply these two to get P02 by P1. So, that number and multiplied comes out to be 4.22, this is one case. Now, I will guess something higher, I do not know whether I should guess higher or lower right now, I have one number, I know that this is less than this, okay. P02 by P1 is not easy to judge, if I increase Mach number will this increase or decrease, currently I cannot tell very clearly, of course once you solve this problem you know which way to go, okay. Right now I do not know, so what will I do, I will just guess randomly some number, I am picking 2.5, I could have guessed 1.5 also, then I will find that this will be lower and then I have to go higher, then I will go to 2.5, that is fine. I am guessing 2.5 right now, and this number is 0.5, this number is 1 by 0.0585, I will write it clear, 585, and so this total comes out to be multiplication comes out to be 8.55, that is this. So, this is higher, this is lower, my answer is somewhere in the middle, so I have to guess something in between these two, I can guess or I can use interpolation between these two, of course we know the function is not linear, but I can interpolate between these two and get to some other Mach number that will be closer, I can do that, okay. Let us say I do not do that, I will just guess something, it looks like the answer should be closer to this number than to this number, because we want 5.65 and this is 8, so it is more close to this number than that number in a way, but somewhere close to the middle, okay. So, it should be somewhere in the middle, but more close to this. So, let us say I will guess 2.1, so in here I have guessed 2.11, I do not know why, okay. To be correct I will keep it 2.11, I have interpolated also, so anyways we will do it this way, I am picking this number that comes out to be 0.67 and this one will be 1 by 0.108, okay. And typical mistake in exams will be this, the tables will be giving P by P0 and you will write P0 by P as that value 0.108 instead. So, be safe about that, you should always be clear about what you are writing, which number you are getting from the tables and what you want, okay. And that comes out to be 0.108 and this product comes out to be 6.2, okay. It looks like we are closer, but I am still not close to the answer, okay. But it is getting closer, it is pretty close to the answer compared to this one. So, I will go lesser, so the next guess I will go 2. It so happens that I know the answer 2 because I had other tables, but if I do not know, typically I would have guessed 2 directly here, next number, okay. But I just wanted to avoid 2 for some time so that you know the iteration process. So if I pick this, that number comes out to be 0.721, 1 by 0.128 and 5.63 comes up there, okay. 5.63, but we want 5.647, not exact answer, okay. So answer is somewhere in between these two, but very close to this. So I will try one more, 2.01, and see what that looks like. If I pick 2.01, this is 0.716, oh I put 716 and 1 by 0.126, and the number comes out to be 5.68, okay. I want an answer close to 5.65, so it is more close to this than to this. So I can go and interpolate between this and say the answer should be 2.007 or something like that, 2.003 or something, or I will just leave it as 2. So we will currently do that and say answer is just 2, okay. So my M1 or the Mach number in my test section happens to be 2.0. If you want, you can be more clear and take an interpolation between this and it will be what, 2 out of 5 in that gap, that is 40% from here to there, it will be 2.004 if you want, or I will just give it as 2, okay. If I am accurate enough up to second decimal place, that is enough, that will be 2.00, third decimal is 4, I will ignore that. So I am getting number Mach 1 as 2, okay. This is one way of doing it. Typically when you are solving such a problem, I would start guessing with 2, guess nice numbers like 1.5, 2, 2.5, that kind of numbers, okay, nice way to guess. Once you guess that, you will finally go to a point where the answer is between 2 of them. You could directly interpolate, but I would not, I will go pick a number that is nice, something in between, and I will get much closer to the answer like this. I can interpolate at this point, but I know the answer is very close to this, so I will guess something in between this but very close to this. I am very close to the answer. At this point I can interpolate. This way you will solve the problem faster than if I start interpolating here, it will go somewhat close to the answer. I will tell you what it will be also. If I interpolate across here to get to this number, I will get 2.2. So then I will find that the answer is between 2.2 and 1.7. If I interpolate between those two, I will get 1.91. Okay, so its answer is between 2.2 and 1.91. Okay. If I interpolate between those two, I will get 2.11. That is how I have this number in my chart. I did the full interpolation method. Okay. 2.11 you will get. Now I know the answer is somewhere between 1.91 and 2.11. Now I will go and guess 2. That gives me this number. I find that it is close but slightly less, so I will guess something higher, I will get to this answer. Ideally I will guess, then interpolate. Guess 3 or 4 times, then start interpolating, that is easier. That way you will solve the problem faster, you won't waste time in exams. Go to the next one, another problem. Now it is more of practical problems. I am having a cylinder moving in still air at Mach 2 speed. I am having a cylinder, we are looking at a 2D problem. This dimension is infinite, minus infinity to plus infinity, okay, and this is moving at Mach 2. What does that mean? If I shift my reference frame to this on the cylinder, then I will remove this arrow here and I will say my flow is coming in with free stream Mach number of 2. This is what we are having, and as I already told you, if I put any object in flow, in supersonic flow, there will be a shock in front of it. Okay. Now we are interested in finding the leading edge, I will call it the point A. I am interested in finding pressure and temperature at that point A, PA and TA, that is what we are interested in. If I am trying to find that, it is a simple enough problem. of course I have to first cross the shock. The streamline that is going straight there will be the streamline that is going to cause the pressure there. So across the shock, of course P naught drops, but T naught stays constant, Mach number drops. After that the flow is subsonic. Now if I look at flow around a cylinder, subsonic flow, it will achieve stagnation pressure at the tip, at the frontmost point, which is what we are interested in this problem. So I am going to say it will reach the stagnation condition P naught 2 for this shock and T naught 2 which is equal to T naught 1 for any normal shock. So I will end up like this. Of course remember it should be stagnation conditions, stagnant shock, then only T naught 2 equal to T naught 1. We just did moving shocks and we saw that T naught 2 by T naught 1 is not 1, it is more than 1 always. Okay. That is why we shifted coordinate system. Now the shock is stationary in front of this cylinder, and so I will have T naught 2 equal to T naught 1. So I just have to solve this problem. So I need to know P naught 1 and P naught 2, P naught 1 and T naught 1, sorry. That number, that information is given in the question itself. P equal to 1 bar, T equal to 300 Kelvin. Our somewhat standard conditions I am getting these numbers. Okay. These are static conditions, not stagnation. So I have to find the stagnation conditions for M1 equal to 2. Okay. So if I do that, okay, I have to find P naught 1 by P1 for M equal to 2 and T naught 1 by T1 for M equal to 2. I can find these numbers, okay. And once you know this, all I have to do is I will find P naught 1 from this, okay. P naught 1 is known, T naught 1 is known. If I know these two numbers, all I have to do is T naught 2 is same as T naught 1, this is directly your answer, pressure and temperature at that point, temperature answer is directly there. Okay. If I want to find P naught 2, I have to go to my tables and look for normal shock tables, M1 equal to 2, that particular condition P naught 2 by P naught 1. Okay. I can do all this or I will take a shortcut. It so happens that my tables has, I can do this is one way of solving, but I do not have numbers for this in my page. I have in my tables P naught 2 by P1, okay, which is very useful. Okay. I am given P1, I want P naught 2, I have already gone through that discussion. So all I have to know is this number for M1 equal to 2. If I have this, then, and of course it is M equal to 2, we just solved the problem, it is the same number 5.647, 5.641 apparently for M equal to 2. Okay. So I am getting this number here. Okay. Now from here P1 value is given to be 1 bar, so I will directly get this number to be 5.64 bar. Okay. P at A equal to P02 equal to 5.64 bar, that is what you are getting. What about T naught? Let us find it. T naught 2 equal to T naught 1 is equal to T into 1 plus gamma minus 1 by 2 into 2 square, that is all. It is 300 into 1 plus 0.2 into 4, that is 1.8 times 300, 1.8 times 300 is 540, 540 Kelvin is the temperature experienced and the pressure experienced happens to be 5.6 times the atmosphere. These are the rough numbers which the cylinder faces at the front. This is why you have to worry about high speed flows, everything will experience much higher pressure than what is really happening there, because it is moving faster, your stagnation conditions are very high. If I move at Mach 10, the temperature will go crazily high. If I use gamma equal to constant and find the temperature, it will come to 10,000 Kelvin or something, very high number. Let us just look at that number here roughly. If I put 10 here, it will be 100, 100 times 0.2 is 20, 21 times 300. Oh, it is not very high, it is 6300 Kelvin. Okay. But I already told you more than 2000 Kelvin gamma will start changing for air. So, that number is not correct. I have assumed gamma equal to 1.4 here, that number will not be right. Okay. Number will come down a little bit, it will come to probably 4800 or 5000 Kelvin, but we will not worry about that for this moment. We will say in our world it is all nice. Okay. Now, I want to look at the same problem in a different form. Now, we are going to look at moving shocks. It is the same problem, cylinder. Now, I am going to say that the shock is having the same strength, P2 by P1 is the same as this case, and so it is having the same strength, m shock equal to 2. We already solved the problem partly. I am going to look at it from moving shock perspective, okay. And because of that, if I look at it from outside reference frame, it will look like this Mach 2 shock is moving into still air, V1 equal to 0, Mach 2 shock is going this way. Okay. I want to solve this problem. First thing I want to do is find the shock speed. Shock speed is nothing great, I know V1 is 0, I want to find A1, cylinder is still here, okay. We will keep the cylinder also. A1, we said it is 300 Kelvin, so it is 300 Kelvin and air 288.6 into 300. This happens to be 348.2 meter per second. You can call it 348 meter per second if you want, it is fine. Okay. So, my shock is moving at Mach 2, so it will be double this number, 2 into A1, which is 696.4 meter per second. This is my Ws, I used to call it Ws, so we will keep it Ws, speed of the shock with respect to my outside reference frame. This is my moving shock. Shock is moving into still air. Now, I want to find the velocity behind the shock caused by this shock. Okay. So, we have directly one formula, we will just use it. I am going to say P2 by P1 is what is given in the formula, right. In all our formulas we had P2 by P1. So, I will find P2 by P1 for m shock equal to 2, it happens to be 4.5. Now, I will use this number in my V2 formula in my shock calculations. If I use that, it is A1 into gamma plus 1 by 2 gamma P2 by P1 plus gamma minus 1 by 2 gamma to the power half into 1 minus gamma plus 1 by gamma minus 1 plus P2 by P1 gamma plus 1 by gamma minus 1, I think that is multiplied by P2 by P1 plus 1. This formula we already wrote, I think 2 classes back. Okay. You are having this. Now, all I have to do is substitute numbers for this. By the way, I should get used to gamma plus 1 by gamma minus 1 for gamma equal to 1.4. We already did the number. What is that number? 2.4 by 0.4, 6. Okay. It will be 6 plus 4.5 divided by 6 into 4.5 plus 1, like that you will get. And here it is gamma plus 1 by 2 gamma. We will write the numbers anyway, 348.2 into 2.4 by 2.8, 24 by 28. Okay. So, that is 24 by 28 is 6 by 7 into 4.5 plus this is 0.4 by 2.8, 1 by 7. You have to get used to these kind of numbers, it is not very difficult. To the power half into 1 minus, we already know this number is 6, 6 plus 4.5 divided by 6 into 4.5 plus 1. You have to just calculate this, nothing more to simplify here. Okay. And that number happens to be 435 meter per second. Okay. Now my critical question, what is the velocity of the cylinder with respect to my outside reference frame? We said that was moving at Mach 2, which means that will be equal to 2 times a1. This is not equal to 2 times a1. 2 times a1, I will just write velocity of cylinder. V cylinder is equal to 2 times a1 as 696. Okay. V2 happens to be this value. So what is happening? This is your physical intuition part. So now I am going to say there was a shock. After the shock, I have velocity 435 meter per second. Sorry, it is not this way, it is the other way, arrow is other way. Shock is going at 696 meter per second, and gas is going with 435 meter per second, and there is a cylinder which is also going at 696 meter per second. So if I suddenly switch to the other reference frame, what will happen? Shock is stationary with respect to this cylinder. Okay. If I say the shock is stationary with respect to the cylinder, there is a velocity of this fluid with respect to the cylinder. How much is that number? Actually it is 261. 261 meter per second. Okay. This is what is the final flow around the cylinder. This is what is going to go like this. Okay. That is why you have to get used to the problem from both points of view. Whichever reference frame I am in, I should be able to solve the problem. Okay. The shock is such that this flow around the problem will give you a steady state. Okay. It so happens that shock will stay stationary at some particular distance from the body. There is something called a shock standoff distance. We will not deal with it now, we will go deal with it when we have bow shock. We have not gone to bow shock, we are still in normal shock and moving normal shock, that is what we have done till now. Okay. And shock standoff distance is decided by how much mass flow rate has to go through and turn around the cylinder, is it having enough space and all that. Okay. I think I have time only for one more problem, and with that we will stop. I have a lot more questions that is possible. Okay. I will just modify this question to a spherical bullet. I am shooting a bullet at supersonic speeds into still air. Okay. Spherical bullet, for our plot it is still looking the same, and of course it is going to have a shock in front of it. Okay. And we are interested in the same front point A, we want to find pressure temperature there. Okay. The question is asked differently here, but it is still the same thing. What is the pressure and temperature at the leading edge? But of course from our discussion we know that we are looking for P02 and T02. This is what we are asking essentially. Okay. And of course you have to be given all the information. I am going to tell that the bullet is moving at 900 meter per second. Okay. So it is, if I go to other reference frame where flow is coming and this bullet is stationary, this is coming at 900 meter per second, and it is given that it is at 10 kilometer altitude. So I am at 10 kilometer altitude, and that is like typically the altitude of aircraft flying long distances. Okay. At 10 kilometer altitude I am shooting a bullet at 900 meter per second. I want to find the pressure and temperature experienced by the front end of the bullet. So of course you need to know information about atmosphere. Several tables exist. Typically if you take separate booklets which are gas tables booklet, like so many authors are there, I do not want to name any one particular author. So if you pick any of that, then you will also get standard atmosphere tables. We will use standard atmosphere. I will give you the values. P1 is equal to 2.64 into 10 power 4 Pascal and T1 equal to 223 Kelvin. Standard atmosphere tables are also available separately. It may not be available in typical compressible flows books, but if you have separate gas tables or compressible flow tables as a book, there you will have standard atmosphere tables as the very first table typically in most of the books. You will have this also. So, once I have this, I have P1, okay, and I have to find the bullet speed. Okay, 223 Kelvin if I pick, A1 is 1.4 into 288.6 into 223 Kelvin. It comes out to be 300.6 meter per second. We will make it 300 meter per second, some such number. It is almost 300 meter per second. This says that my M1 happens to be 3, okay, because it is 900 meter per second. M1 happens to be 3. Now, the problem is simple. I just need to find P02 by P01. So, I will get the answer directly P02, because I have, I do not have P01 yet, I have P1. You have to find P01, but it is similar. Okay. Of course, I have my special tables where P02 by P1 is given. I can just go multiply the P1 and I will get answer. Let us say I do not go that path this time. Okay. I want to find P0 by P for m equal to 3. How will I do it? If I do it by formula, it is going to be 1 plus 0.2 into 9 to the power gamma by gamma minus 1 is 3.5 for gamma equal to 1.4. Okay. I just have to find this number. It is what, 1.8, 2.8 to the power 3.5. That number happens to be 36.73. If I go look at the tables also, I will get the same number. Isentropic tables for m equal to 3 will give you this number if you go to gamma equal to 1.4 tables. Okay. So, I have to find P0, which is 36.73 multiplied by P1 given there. P01 is equal to 36.73 multiplied by 2.64 into 10 power 4 Pascals, which is 9.7 into 10 power 5 Pascals. It is roughly 9.7 atmospheres. That is what you are getting. This is P01. So, P02 is equal to P01 into P02 by P01 for m equal to 3 from normal shock tables. So, that is 0.3283 multiplied by 9.7 into 10 power 5. Answer is 3.18 into 10 power 5 Pascals. This is the pressure experienced by the leading edge of my bullet. What about temperature? T0 by T for m equal to 3, which will be 1 plus 0.2, which is gamma by gamma minus 1 by 2 actually, okay, multiplied by 9, which is 2.8. So, T0 is equal to T times 2.8, T02 equal to T01 for normal shock, for stagnant normal shock equal to a stationary normal shock, better word, okay, which is equal to 2.8 into T1. That number happens to be 624.4 Kelvin. These are the various ways of solving simple problems. Next class we will go and solve more of moving shocks. Okay. This we had one problem solving moving shocks, but we directly used the formula. Okay. But this formula will not be easy to handle, it is more difficult. We will just start using intuition and normal shock tables from next time. Okay. That is a better way of solving, you do not need to remember such formula anymore. Okay. we will see how to solve that next class.